Section 11.4 is tangent planes and linear approximations. And this will be very similar to linear approximations for functions y equals f of x or single variable functions, where we talked about tangent lines. So all the analogies or analogs that we could think of here will come to bear, and we'll even see a few diagrams of this situation as well. So the equation of a tangent plane to a surface. So again, remember that a function f of xy is a surface. Z equals f of xy's graph is a surface in three-dimensional space. If such a function has continuous partial derivatives, so f sub x and f sub y are continuous, particularly at the point x naught, y naught, then the tangent plane to the surface z equals f of xy at the three-dimensional point x naught, y naught, z naught is given by the formula below. So z minus z naught is equal to partial of f with respect to x evaluated at the point times x minus x naught plus partial of f with respect to y evaluated at x naught, y naught times y minus y naught. Okay. Compare this to what we used to do in Calc 1. Just for a quick note, Calc 1, our linearization looked like this. Y minus y naught was equal to the derivative of f at x naught times x minus x naught. This is essentially the same thing, only y is now an independent variable. Z is our new dependent variable, so we have to include y's derivative. To do so in a way that makes sense, we have to use partial derivatives, so the direction along, or the derivative along the y-axis, or in the y direction, and the derivative f of f only along the x-axis, or in the x direction, or in the x component. So that is the analog to Calc 1 in this situation. So we can start out simply with this. We'll just calculate the equation of the tangent plane, and this is just formulaic, just to see how we might use this. We'll recognize that if we're given a function z equals some expressions of x and y, then we know that z, of course, is f of xy. So when we go to use the formula above, there's no confusion about who is who. So we'll take the derivative with respect to f of x of this whole expression on the right. Remember that in this situation, partial with respect to x treats y as a constant. So when we take that derivative, we'll find f sub x is 6x minus 1. That's because that's from this term here, and that's because this term is a constant with respect to the partial derivative with respect to x. So it just differentiates to 0. Similarly, f sub y treats this as 0, or as a constant, so it differentiates to 0 as well as this, and we're really only differentiating this. The only term that survives is 2 times 2 times y plus 3 times 1 for the chain rule on the end here, even though that's not necessary. It doesn't really change it, so it hasn't been written in. Now, plug these things in, f sub x and f sub y. This is our evaluation at the, so inputting our point x naught, y naught, z naught. So as follows, 2, negative 2, and 12 is the point given to us in the problem. That's where we want to create this tangent plane, just like where we would have wanted to create a tangent line back in Calc 1. So x naught, y naught, z naught. Fill in this formula as we see here. Here is evaluation at x naught, y naught. Evaluation at x naught, y naught. This is z naught, its role as well. And we have x minus x naught, y minus y naught. Those in those components. Simplifying this, we of course see the equation of a plane coming about. That should always be the case. Of course, it's always the equation of a tangent plane to a surface, so we should always have a plane as our result. If not, we know we've made a mistake. And combining all this in the standard form of the equation of a plane, we get what follows below. Now, off to the right, there's a sketch of this situation. It's not exactly the plane that we have right here, underlined in blue. And remember, we're not terribly interested in exactly sketching any of these graphs, but understanding what these things represent is the important part. In blue is the graph of z equals f of xy here. Notice that this is, when we look at each of these terms, this is an elliptic paraboloid. We classify it. It happens to be a quadric surface. That's useful. We know more or less what it looks like. That's why we learn those surfaces, so we could at least have examples to look at sometimes. It's been shifted to the right by 1, or along the x-axis positively by 1, along the y-axis negatively by 3, and along the z-axis positively by 7. So I've got a rough sketch of where that elliptic paraboloid is in the xyz plane. It's in blue here, our elliptic paraboloid now. And in red, well, I've tried to plot the point to negative 212 as best I could. So it's more or less here. It's on the surface of that quadric surface, or that elliptic paraboloid. And the plane that we just came up with is, in fact, the plane that's tangent at this point on that quadric surface. So that's, the rough idea of what we're calculating, just like we used to calculate a line tangent to a point on a curve and use that to approximate values on the curve near that point, near this point in this case, for the 2-3D example that we're looking at. We can use this plane to approximate values near the surface, just as we used to approximate values near a curve. So that is a basic sketch of what's going on from the problem that we've just seen. It's a fairly formulaic process to come up with the equation of a tangent plane. Okay, so for a better picture of this, I've drawn this, or selected this from the textbook, or one edition of the textbook. I believe something very similar is in our edition as well. So a linear approximation of z equals f of xy. So again, remember we mentioned that this function here, f of xy, is a surface. Its graph is a surface. Okay, so what we have in the photo here is some arbitrary z equals f of xy. Perhaps it's an elliptic paraboloid. Who knows? It's just some surface that's graphed in 3 dimensions. Now, beneath it in red, corresponding with the same colors I used on the previous page, we have the plane that's tangent to it. And of course, this thing's graph is maybe most fully filled in by saying z is equal to L of xy. Okay, so it's another function of x and y, which z is equal to come up with this graph. It's the and that's the equation of the plane that we have essentially calculated in the previous example. So what's happening in the picture as we move from left to right is we're zooming in on this situation. And this is just to convince the student that as we get closer, so pay attention to the axes here, the scale is increasing or decreasing, right? We're zooming in closer and closer. Instead of going from -4 to 4, we're going from -2 to 2 in picture B. Okay, as we get a little closer, we realize that the difference, the gap between the surface and that plane is getting smaller and smaller. We zoom in again. Note the scale now is from 0 to 2, so half of what the previous scale was. And we see that there's very little error. This fits the same scheme that we saw back in Calc 1 when we approximated a line with, approximated a curve with its tangent line. If we look at this range, we zoomed into this range in this photo, this graph down below, we'd realize there's a little bit of error, but the line is somewhat close to that curve. The line standing in place of the plane now, and the curve being a curve rather than this surface. Zoom in a little further, we get a little better. Zoom in even further, and it looks like the line is very close to that curve, and it's a useful approximation in a neighborhood of that point. One more thing that I can point out, at least in this picture, is that this is our point, at least in this case, this is the point x naught, y naught. Above, somewhere in that photo in this plane, there's a point, or the photo in this 3-dimensional space, there's a point here where that surface is tangent to its tangent plane. And that point is x naught, y naught, z naught, representing the all the points involved in graphing this. Okay, so there's your analogy. That's what's going on when you're calculating these tangent planes. Of course, the main idea is that the closer we are to our point of tangency, the better our approximation is. And that's always been the case, and that will continue to be the case. Moving a little further, now we can talk about a linear approximation, using that tangent plane to approximate the value of the value on a surface. Okay, just like we used to use a tangent line to approximate the value on a curve. Now the only difference is, of course, this is our value of f. It's like f of x naught in the linear case, or in the one variable case. And here we've got the x component, the derivative with respect to f at x, evaluated at our point, times x minus x naught to help form part of the plane equation. Our y component similarly is done, partial with respect to y of x naught y naught times y minus y naught helps to build out the rest of the equation of the plane. So again, I'm pointing out, I'm saying helps to build out the equation of the plane. What I'm really trying to emphasize there is that this is a variable and this is a variable. And when we're done using this linear approximation or building one, those two things should remain variables, and there shouldn't be any other variables other than perhaps z itself, which can just be z equals the linear approximation L of x, y. Okay, and that's how we'll have a plane described in these spaces. Okay, so let's look at an example below. Compute the linear approximation at 0, 0, so this is our x naught, y naught in this situation, of the function u equals square root of y plus cosine squared x. So we could call it z if we wanted to as well, change its name if that would be helpful, but it's a third variable. It'll represent a third component just as well as z will, so that's fine. We can be in the x, y, u space instead of the x, y, z three-dimensional space. Anyway, we use this linear approximation to estimate the value of u at the point 0.1, negative 0.1. Okay, so we're going to build our linear approximation around the origin, or the point 0, 0. And we notice that the point 0.1, negative 0.1 for x and y, or for an xy coordinate, is not too far from 0, 0. So it's probably a reasonable point to approximate the value of this function through this linearization function at. So it's a good candidate. If it was 10 comma negative 10, it's pretty far from 0, 0, and it might not be a very reliable approximation. So the closer you are to your x naught, y naught point, the better your approximation will be. And you should really kind of stick to working close to these approximations. So to build our linearization, we use the formula above, L of x, y, right? And filling these things, well, we know that we'll need the first derivative of u and x, and we'll need the first derivative of u and y, partials for both. So the partial of u with respect to x, given here, is a matter of chain rule out here for this power of 1/2 to come down, raised to the negative 1/2, sorry, product rule first, negative 1/2. Then the chain rule tells us times the derivative of the inner function, and that comes out to 2 cosine x times the derivative of cosine x, so another chain rule, and that gives us negative sine x as another factor right here. So product rule on the outside and 2 chain rules to follow up. And that is u sub x. We've simplified that function a little bit further right here. Luckily, we're going to evaluate that function at a point x naught, y naught, which is 0, 0, and it'll clean up that mess a little bit for us as we proceed. U sub y, calculating this partial derivative. Again, outer chain rule, 1/2 comes down, and we're raising to a negative 1/2 power. Now we partially differentiate with respect to y, so cosine squared x is now a constant, and our multiple is just partial derivative of y with respect to y. Well, that's just 1. Cosine of x, so cosine squared of x has a partial derivative of 0 with respect to y. So now we have u sub y, or our partial with respect to y. And for both of these functions, we're going to plug in x equals 0, y equals 0. In this function, we get 0 because sine of 0 is 0, and that's times the entire expression. So we know that that zeroes out completely. So we'll mark that. And then for use of y, plugging in x equals 0, y equals 0, we get 0 plus cosine of 0 is 1. 0 plus 1 squared is 1. Inside these parentheses, raised to the negative 1/2 is 1 again, and then 1/2 times 1 is 1/2. So those are the details on that. And once we have our values for use of x and use of y at 0, 0, those being 0 and 1/2 respectively, as we've seen above, we can plug those into the expression for L of xy. And I've marked that this linear approximation is for the plane tangent to the curve at the point 0, 0. So it's not bad to denote where this linear approximation was formed or what point it's based off of for reference and using it later, and to make sure that we're using it on a point that's close enough to our 0, 0 point, or where we based our linear approximation for an approximation of the function overall. So plugging these things in, we have, this is z naught right here. Okay, and z naught was obtained by somewhere above, I believe we have it. Z naught is here. U of 0, 0. So I will label it as such so we can see that as well. Z naught, or really in this case, U naught is a better name for it, but just so it matches terminology from above. Or f of x naught, y naught, same thing. So I'll add one more note. This is f of x naught, y naught. Okay, so that's 1. We did that at the very beginning, just forgot to mention it. And of course, we could do that later as needed. It wasn't necessary for the partial derivative. So that is our f of x naught, y naught. Then we have the derivative, the partial derivative of f with respect to x evaluated at 0, 0, and that came out to 0 as we saw just above. Similarly, and then it's times x minus 0, 0 being x naught. And then we have 1/2, that's the partial derivative of f with respect to y, that was over here. And that was 1/2 times, what do we have in this is y minus y naught. Again, y naught is 0. And what we see is that, as I was saying before, x and y remain as variables in this, so the only variables that should remain when we build these linear approximations. And our result, once we simplify this, is 1 plus 1/2 y. So that is our linear approximation at the point 0, 0 of the function u equals, well, all of this expression here. What we'll note is that our linear approximation is much more simple looking than our original function. This function down here is much easier than u equals to the one, a function to the 1/2 power of y plus cosine squared x. So it'll be a lot easier to approximate values of u than it will be to actually plug numbers into this function u and evaluate. That is one goal of these approximations. That's one thing that makes them useful. Oftentimes in the real world, we can't get exact values of things, and we have to approximate. Our use of pi and day-to-day, calling it 3.14, is merely an approximation of an infinitely long, non-repeating decimal number. So approximations are prevalent in mathematics and science and engineering. Now, let's use this. They actually ask us to approximate the value of the function. So let's demonstrate how well this approximation can go. We need to approximate the value of u at 0.1 and negative 0.1. Okay, so down below, we just simply plug in 0.1 comma negative 0.1 as our xy values in our linear approximation at 0, 0. And that's plugging them into, well, what we see above here is this function. So the x-coordinate doesn't matter. It doesn't play a role in this. It just happens to have a slope of 0 if we think about that in terms of the direction numbers for the equation of the plane. So really, the only thing that shows up in this calculation below is the y value. And we have 1 plus 1/2 times y. This is our y value of negative 0.1. And then that's equal to, well, 1 minus 0.5 times 1. Simplifying all of this, we see that our linear approximation near the 0.00 of the value 0.1, negative 0.1, is 0.95. So what we would assert at the end of this, and we'd assert it reasonably confidently, that f of 1 common negative, or 0.1 common negative 0.1 is approximately 0.95. Okay, now how accurate is that? Well, now we can loosely say, since that point is close to 0, 0, this is probably pretty close to 0.95. But in terms of, there are two parts of approximation. One is to get an approximate answer that you'll use, and two is to know what error might be in that. So the rest of this section is dedicated to differentials, increments, and essentially both of these things are measuring error and approximations. Also, they're setting us up to define differentiability in functions of multiple variables. So we'll see that in the next video.